Hello, welcome. In this video, we will present the algorithms for finding prime numbers. Prime numbers have many applications. There are a lot of research undergoing to discover large prime numbers. Here's the website that gives awards for the discovery of very large prime numbers. We know what is a prime number. We have written programs to find prime numbers. It's not difficult to write this kind of program to find prime numbers, but it's not easy to get a very efficient algorithm that discovers large prime numbers. In listing 5.14, we present a brute force algorithm for finding prime numbers. The algorithms checks whether 2, 3, 4, 5, or n-1 divides n. If not, n is prime. This algorithm takes all of n time to check whether n is prime. We can easily improve it. Just note that you only need to check whether 2, 3, and up to n divided by 2. You don't have to go beyond n divided 2 and check all these numbers if they divide n. If not, n is prime number. Well, the algorithm slightly improves, but it's still in the order of the same magnitude, order of n. In fact, we can prove that if n is not a prime number, n must have a factor that is greater than 1 and less than or equal to n square root. So we can prove it, and using this observation, we can improve the complexity and make it the time complexity to order of n's square root. So this is much better, but we can do even more better. So let's go in further, and we're going to go further and to look at another way to do it is we don't have to check all the numbers 2, 3, 4, 5. No, we check the 2. We don't check a 4 again. So we only check the prime numbers before n square root. See if they are the divisor for n. So that is, here is the improvement. And this is the another way to do it. This is much better. And using this algorithm, we get the complexity is order of n times n square root divided by log n. There's another way to do it, and that's the way. It's a very well-known algorithm. It's called the sieve of Eratosthenes. So this is the one is you're using a table here. So let's illustrate it. And here is for the so the numbers here, and we look at all these numbers. So this is going to be very, very large one here. And so we only show the first part of it. And so we're going to initially, we're going to have this, the array. So here, using the array primes, and we're going to set this all to true. And now we go with the prime numbers here. This is the k is 2. So look, this is divisible by 4. And so I'm going to set to false, 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 false for 3. And so this is the 9. So it's a false, false, 12. And this is the 15, false, false. And for k is 5, so we're going to get the false here. It's so this is so this is the 15, okay, and 20. So all this is a false. Now what is left? You can see this is already true. So this is a 2 now is a prime number, 3 is a prime number, and 5 is, and 7 is, and 11 is. So that's how you eliminate the numbers they're not prime. And so what is left? And that is prime. Okay, so when you set this, the prime to false is for this 2, you're going to go with the index. So this is the 2 times 2, and that is false, and 2 times 3. So this is 2 times 4 and 2 times 5. So that's how you're going to get this, the array primes to set to false. So we're going to look at this implementation for sieve of Eratosthenes. And so here we're going to prompt user to enter n. So we're going to find all prime numbers less than or equal to n. And so these are the prime. So this is right now it's empty list of prime numbers. So here we're going to append this all for now. So we're going to have this is make all true for this. It's I is in this range. So from 0 to n. And now look at this and k here. So for this k is less than or equal to n divided by k. So that's how you need to look at it. And up to this, if this primes k, that's true. So we are going to do this, set all of this to false, k times I. So after this is finished, and now we can print the prime numbers. So we're going to look at this. If primes brackets I, and this is true, so we're going to count the number of primes and display it. And so we're going to display this 10 numbers per line. So this are all the prime numbers and 10 numbers per line. So it's all displayed right here. And so the total here we have, so we have this n is 1000. And so this is 168 prime numbers. Now for this sieve of Eratosthenes algorithm and the complexity, it's actually the same as we had before. It's order of n, n square root divided by log n. But this is very loose bound. This is actually a little better than we have in the previous algorithm. And here in this table, it summarized the time complexity for various prime number algorithms. So this is the very early one we have. And to find all the prime numbers up to n. So this, the brute force algorithm takes order of n squared time. And this, if you only go to n square root. So that's what you get out of n square root time. And now if you only consider the divisors of the prime numbers, 2, 3, 5. So this and here, it's the complexity, it's n times n square root and divided by log n. So this is the same complexity as the sieve of Aristoteles algorithm. That is all for this section. Thank you for watching. See you on the next video.